Hello, everyone. Welcome to Rational Science live from Frankfurt, Germany. Here I am with my son, Hans.
Hey, guys.
And we're going to be doing a little review of this month. We're still in the month of February. And then from there, I'm going to move on to answer some of the questions that people made throughout the week since last time. And the last part, we're going to open the floor for questions and comments, I guess. My son Hans is going to read them out, and I'll do my best to answer them. If I can't answer them today, you got to take a rain check, and I'll mail you the checks in the mail. Okay. So let's get started here. I'm going to start with a summary. Here it is. And what we covered this month, or where we started with creation and chronology of what? Of matter, of how matter came to be. And we started with a question: why is there something rather than nothing? Okay, question that a lot of people typically ask in so-called physics, so-called science. What's our answer? Well, here's a quick reply to that. Okay, it's an irrational question. That's what it is. Okay, it's an irrational question because the person is framing questions of philosophy, reasons, and purpose, why someone does something, in the context of physics, in the context of mechanisms and causes. That's the problem. The person who says, why is there something rather than nothing, is summarily introducing God into the picture, saying there's an intelligence out there that had a reason for creating something rather than nothing. Okay, that's in general the issue. Now, physics tries to concentrate on mechanisms, and for this, these people usually try to come up with some kind of mechanism that would produce something from nothing. And all I can tell those people is good luck. Here's as you can see, point number 2 there, God versus the p-instanton. Well, this is what Christianity, I guess the primary religion in the West, and science essentially propose today. We have what we'll call religion. There's this God, this being that's been there forever, I guess, and he created the universe. That's it. Doesn't get any better than that. We get that from the Bible. And then in the case of science, so-called science, we have the p-instanton. And so what is this p-instanton? How do they explain something from nothing? Well, in the traditional Big Bang theory, you have time rolling at the edge of this cone that is expanding, okay, from ground zero, from the point where... No, it's just that it was, at some point in time, something began, there was an explosion, and from that point on, what we see here in this cone is that time flows along the edge of the cone. That's what they changed, and they created the p-instanton, and what they did here is they rolled around space and time into a circle. And a circle has no beginning and no end, therefore space and time has no beginning and no end. That's the mathematical version of how something comes into nothing. You just put a circle there and you say there's no beginning to the circle, no end to the circle. And you say that space and time are like a circle that forms the bottom of the p-instanton, which nobody knows where it came. They say it's an irrational question to ask, even where that could have come from.
What is the p-instanton?
It's it's the particle that gave rise to the universe.
They didn't have a better name than that?
No, it's the instanton, and then they say it looks like a P, so they call it the p-instanton. Okay, and yeah, I discussed that in previous lectures.
And I assume they don't say where it came from?
No, they say it's an irrational question, unscientific question.
It's unscientific to ask where God came from.
Yeah. Yeah, essentially, it's an irrational question because they cannot test it scientifically. You cannot run an experiment to prove how it came into being.
There's a similarity between them calling that an irrational question and you calling why is there nothing instead of something an irrational question. What's the difference between those two?
Well, let's get back in here for a second, just so. Yeah, it's a philosophical question if you're in other words, phrased in the context of physics by saying, why is there something rather than nothing? Like, why did someone create something rather than nothing? In other words, that's where it's irrational. Otherwise, you cannot explain something from nothing, no matter what you do. You cannot explain the mechanism. That's why they say it's unscientific, because they can't answer that question, never will. And to say that mathematics can answer that by saying that space and time, supposedly mathematical objects or things or whatever, are wrapped around in a circle and there's no beginning and no end to a circle, that's how nothing came into being from something came into being from nothing. It's a word wizardry. That's what it amounts to.
And how do you get around this problem?
Very easy.
Where the universe came from?
Very easy. The universe came from nothing. It's always been there, and it always will be there. There is no creation.
It didn't come from.
Right. So that's the answer. Anyways, there's another version, and here, let me get that back in here. Okay, there's another version, and it doesn't explain the origin of the universe, but it's called the multiverse. There's all these universes out there, and one of those is ours. In fact,
marbles,
yeah,
cat's eyes.
Because those are the cosmic background radiations that they get, and they map them. And so, you can think of them as many cosmic background radiations, one over here, the other one over there. What separates them, we don't know, because the little ball there includes space. So the black stuff is not space. It's the black stuff which they cannot identify.
To clarify, this isn't a picture that they took.
No, obviously.
Is there many pictures?
Yeah, there's many versions of the multiverse, but the point here is that these marbles that you see in there, each one of those includes space. It's space, time, matter, the whole works. And so the question is, what's the black stuff that separates one universe from another? You can't say space because that's what is included in each marble.
Well, obviously it's spacer. It's extra space.
Yeah, it's the fourth dimension.
Thought.
That could be thought. Yeah, I don't know. They have to figure that out. Okay, so moving on here. Let me put this back here. That was the multiverse. Then you have the origin and chronology of particles. How did they come into being? Well, here's their version of the chronology, okay? And it starts with a Big Bang. It goes to the Planck phase, then moves on to the inflationary period, the electroweak. All these are subatomic particles that were created at different points in time until they get to this era here, the atomic period, galactic, where the galaxies were formed, and then the stars, the stellar. Okay, so that's in general their version, mathematical physics version of how matter progressed through the ages. And the funny part about this is that radiation era that you see there, that was in terms of seconds and at most a minute. And what comes after starts at thousands of years, millions of years, and billions of years. So here in the matter era, we're in the billions of years now. Okay, so they jump from seconds to billions. Okay, and that was a little different than what the Christians or religious folk proposed through the Bible, that in 7 days God created all of what exists.
It took longer.
Yeah, and all.
God was kind of slow.
Yeah, and I don't know why he rested, because he's all powerful. Why would he have to rest? But yeah, he took 1 day for each of these things. Okay, so there's a difference in timing from the scientific, so-called scientific version, and the religion.
I love that you compare those two; they're on the same level.
Okay, then we get the problem here is that we get later on into the quasis and pseudos, and I call them the quasis because they're really crazy. Okay, so what are these? Well, we covered a little bit of that, and it's got to do with this. We look at the definition of the quasis and pseudos, and what are they? They are quasi-particles. What are they? They're collective excitations of what? Emergent phenomena. In other words, what you have, like you see on the bottom right there, you see a whole bunch of atoms, molecules, whatever unit you want to use, and they move as a whole. They move as a collection, and they're going to call the collective movement a particle. They're going to say that's a pseudo particle that you're staring at down there. Okay.
What's moving?
Well, what's moving is maybe the atom, the atoms within a molecule, for example. Okay, in that case, you have a crystal lattice. You have the atom moving around a little bit, and the collective movement of this, the whole thing. Okay, they call that a part. They give it a name. They call it, well, it's a pseudo. It's not a particle. It's a pseudo particle or a quasi particle. Something like a concept trying to become an object.
Yeah.
And here you see one of those. The one the first one that I covered was this, the p instanton there. Okay. And then you get this other one, which is the phonon. We covered it the other day. This is a collective movement. Okay. And these are different phonons that you will see here. Okay.
I don't like the term collective movement. That sounds like someone trying to get away with murder.
Yeah, and that's what it is. What you see is collective movement. Each one of these is a different kind of phonon because they have different kinds of vibrations. They require different equations to map these or to represent these. And so each one of these is a different phonon. They say, oh, that's phonon number 1, that's phonon number 2, and so on.
You mean the different sets of movement?
Yeah, there's different sets of vibrations. Okay, so each one of these is a different phonon.
Wait, so the same group of
could
particles could make different particles.
That's one issue. And the other one is that the reason they call them phonons is they say that at the subatomic level, these are producing sound. So the phonon is a particle of sound, a pseudo particle of sound. Okay, each one of these vibrations produces some kind of sound that they are able to represent with an equation. That's how they ended up with these being, particles or
what do they use phonons for?
To listen, they say you can't hear it. You can't. If you don't have
what do they use quasi-particles for?
Again, it's just what they're doing is representing with equations these things so that they can talk about them. And they say, oh, we study phonons. What kind of phonon? We study the A kind or the B kind. The other guy studies the X or Y, Z kind, you know. So in order to publish their papers, what they do is they use these terms which they've created, and they say, well, this one's a pseudo particle. It's not really a particle like the little ball. It's a collective excitation. They're going to group that together, and they say, well, we studied phonon. Which one? Well, we did this experiment, and we found this vibration moving from A to B, and we're going to call that phonon A, and that's the one that moved over. That's the one we're talking about. These other guys, they did another experiment. They talk about the phonon Z.
You know, the beauty about that is if they're moving on to collective motion and calling collective motions new
Pseudo
particles, or they can get rewards for, then they don't have to find new materials. They just take the ones that there are and make different sounds out of them. Oh, this new song here, this is a phonon. This new song here, this is a gluon. But that's the thing. They can invent as many as they want now, because now it's almost like notes in a music piece.
Yeah, essentially,
they can invent as many as they want.
This creates job security for a lot of people, because all they do is they say, well, I'm going to study phonons. And what kind of phonon? Well, I study these vibrations that go up and down. The other guy says, well, I study the ones that go horizontal, back and forth. And so as long as you can put that in that context and say, well, I'm going to study the horizontal, the other guy, the vertical phonons, well, they have different specialties. I'm a specialist in horizontal phonons. And so they develop equations to map or to represent those motions. And they publish papers on that, and it goes on and on and on. Okay, let's continue here with the final part. The last one, again, is the hole that I covered the other day, and here it is. These are the charge carriers, okay? And what you're seeing there is no longer an electron, a negative electron going from negative to positive pole. You see the opposite. You see an absence of an electron known as a hole, and it's going to the negative terminal, to the cathode, okay? And so they have the flowing of holes. And you say, well, what does that mean? What can this possibly mean? And this is how they do it, because they need to explain things like depletion layers in semiconductors. And in order to explain those, the physical interpretation is that you have holes going one way and positive holes, by the way, because these are positive ones.
Whatever that means.
Yeah, and then the negative electrons go the other way. So they do have flow of electron current, which is positive current, which is holes. And this is more or less what it looks like. I saw this in this is where you get it. This is in a Bugs Bunny cartoon, okay? You see the hole moving. Okay, so this is what we have. This is what science has become, okay? Okay, so that's where we ended in general. That's a summary, okay, what we had.
You didn't get a lot done in February, did you?
Well, no, because it was all pseudo particles and creation of particles that we don't know how they were created, because again, they don't want to answer what happened in frame number 1. They start at frame number 2, which is the Big Bang. And you say, okay, but what happened in frame number 1? The one in the movie right before that. And they say that's an irrational question. It's an unscientific question, because we cannot possibly know how time started. And then you still have some mathematicians out there like Hawking and Turok, and they go out there and they say, well, we know. Oh, how do you know? Yeah, what we did, we wrapped around space, around time, we made them into a circle, and there's no beginning and an end to a circle, so that's...
What does that even mean? That doesn't mean anything. Just because it's a circle, where'd the circle come from then? How about that?
It's a geometric
But it feels
theory.
like a double standard going up to religious people. Not that I'm defending or anything, but it's just weird that they would be like, oh, well, where did God come from? Well, you got the same problem.
Yeah. Essentially, one half of the world laughs at the other half. That's all we have.
Yeah, it's two halves laughing at each other. In fact, I think a lot of creationists also kind of get off on it, because they say, oh, well, you're just doing God with extra steps.
Yeah, essentially that's what it is. They are doing God with extra steps, but see, they have the nerve to laugh, because most of these people are atheists, and so they don't believe that there's a God out there, but their explanations are just as fantastic, or even more fantastic, because I can imagine God. And the guy says, look, God's eternal. You got to take that as a given. Okay, I'll accept that. But then I can imagine God with a magic wand creating whatever he wants, even though I can't imagine the mechanism of how from nothing he creates something. But I can understand God doing magic and creating all this stuff. That part we can all visualize. What we cannot visualize is something by itself arising from absolutely nothing. And when you ask the guy, well, how did that happen? He said, that's an irrational question.
At least God
the
was
buck
there.
stops there.
At least God was there. You can push the blame off to God, but something coming from nothing is like, okay, dude, does that just happen?
Yeah. Okay, so let's move on to the questions.
Real quick, wouldn't that mean that at any moment, at any given moment, another Big Bang can come out?
Yeah, that's the multiverse. The version here where you have, where was it? Multiverse here. That's this version
Is
here.
that how they explain that?
Yeah, they say that all these big bangs pop into existence, trillions of years, whatever, then they go out of existence, then they another universe pops up over there, and another one over on the other side. And ours is one of those. That's the explanation they give you. But they don't have, the people who propose the multiverse They're not into creationism in a sense of saying that they can tell you what is in frame number one. They cannot tell you what the mechanism is for one of these universes to pop into existence. Now, don't put it beyond them that they might do it like today we explained, for example, the creation of solar systems, which is there's an explosion of a supernova, which is a big star, essentially. It explodes and it shoots all this matter out there that somehow coalesces, begins running around itself with gases and so on, and that eventually condenses into a solar system.
But that's just matter moving from one place to another, right?
Yeah, and that's what I'm saying here, the same thing. Here you have a universe, let's assume, right? And maybe there's an explosion, or maybe it drifts apart, and whatever matter is in there forms another universe over there. Maybe. Don't put it beyond that they're going to come up with something like that from the multiverse idea. They say, well, it's all these multiverses, they just explode or they drift out of existence, and the matter that came out of existence there forms one universe over here, another one forms over there. So that might be the next great theory of relativity. Okay, let's get on with a question. So we move on here. Issues. One fellow put this issue here. It says, nowhere does quantum mechanics say that particle actually travels all possible paths. Nowhere. If any so-called physicist says that, then they don't understand quantum mechanics. Whoa, okay. The fact that this canard is repeated by clueless dissidents, such as yourself, moi, okay, is a source of amusement to the physics community. Your dumbest followers, that's you, won't know any better when you feed them this tripe. But real physicists get a chuckle out of your inane, uniform rants. Okay, so this is what these guys are saying, what this fellow is saying. Okay, let's find out what the answer to that is. He says that there is essentially, that there is no such notion in quantum mechanics that a particle actually travels from A to B through all possible paths. And, this has to do with a path integral that Richard Feynman came up with, okay? And what he's saying, so that we put it in the right context, he's saying that a particle, quantum particle, doesn't go just from A to B like a classical corpuscle, okay? The quantum particle goes all around the universe in different directions and then arrives at point B. So not only does it go straight, but it takes different paths to get to B, and it also goes all around the universe to get to B. And it's not that it can, it's that it does. All possible paths do actually happen. Okay, so let's get that straight. That's what we're saying. So he's saying, no, that's not true. That's idiocy. I agree there. It's idiocy, okay? But let's find out if it's true now. Let's get some evidence here. Okay, here's first piece of evidence. I can get it up there. Okay, here's the first guy. It says, and this is a lady. She's a retired physicist. Okay, she's got all those degrees there. And she says, in his path integral theory, Feynman speaks of a particle that travels from a time-space point, right, to another time-space point. This particle travels on whatever possible trajectory between these 2 points, no matter how irregular is the trajectory. The trajectories are continuous, and they're set visits, in fact, between T1 and T2, all the points in the 3D space. What does he say? So far, so good. Though the abnormal fact in this story is that the particle does not travel one trajectory, after that, another trajectory, and so on, but travels all these trajectories in parallel. That means that between T1 and T2, the particle goes simultaneously along all the trajectories. So that at any given point time t, between T1 and T2, the particle is simultaneously in many points in the space. I didn't say that. This lady says that. You say, well, who is she? I mean, she got it wrong. She's one of those maybe dissidents who got it wrong. Okay, so let's find out. Okay, she doesn't know anything. Let's go with someone a little more important, someone that everybody knows. Here's good old Brian Greene. Okay, I guess a lot of people know him. He's been on TV. He's a guy who's made some documentaries and so on. He says the following. Okay, these are his words, not mine. Okay, it comes out of The Elegant Universe, one of the documentaries he made on so-called physics. Mathematical physics. Feynman took this one step further in postulating that in traveling from the source to a given point on the screen, each individual electron actually traverses every possible trajectory simultaneously. Did I put words in his mouth or anything? It goes in a nice orderly way, listen to this, through the left slit. It simultaneously goes in a nice orderly way through the right slit. It heads towards the left slit, but suddenly changes course and heads through the right. He's talking about the slit experiment, okay? It meanders back and forth, finally passing through the left slit. It goes on a long journey to the Andromeda Galaxy before turning back and passing through the left slit on its way to the screen. And on it goes. The electron, according to Feynman, simultaneously sniffs out every possible path connecting its starting location with its final destination. And you add up the probabilities of all conceivable paths. Did I misread something? Is there something I'm not understanding, perhaps? Well, let's find out. Here's a Greene on Twitter. This is just a month ago. In January, he wrote this, okay? That's his account. You can see he puts an equation there, and he said the following. Here's one shocking thing about quantum mechanics. These are his words. Twitter, 1 month ago. As a particle travels, it explores every possible path, and what we observe is a melding of them all. Did I misunderstand something? Okay, you might say, well, that's Brian Greene. What does he know? He's just a movie star. Okay, let's
We're gonna go through all of them.
no, just one more here. Okay, let's get Stephen Hawking. You heard of Stephen Hawking, hopefully.
Yeah, but
okay?
he's dead. He doesn't count.
Yeah, but he left his will. Here's his will, okay? Here's Stephen Hawking in Brief History of Time, probably the bestseller in so-called physics or mathematical physics for the public. Okay, he says, a nice way of visualizing the wave-particle duality is the so-called sum over histories introduced by the American mathematician Richard Feynman. Okay, in this approach, the particle is not supposed to have a single history or path in space-time, as it would in a classical non-quantum theory. Instead, it is supposed to go from A to B by what? By every possible path. Okay? With each path, there is an associated couple of numbers, etc., etc. Okay, whatever. He's telling you in your face the particle goes through every path. I didn't invent that. I'm just repeating what these people say.
Yeah, but
okay?
who's this guy?
Yeah, who's Stephen Hawking, anyways, right? He was just, the Lucasian professor at Cambridge. And just in case, in a second book that he wrote after this one, because this was like 2010, this second book here, The Grand Design, he says the following. Okay, again, writing on this subject, says, according to the quantum model, however, the particle is said to have no definite position during the time it is between the starting point and the end point. Rather than following a single definite path, particles take every path and they take them all simultaneously. His italics. Is there something I'm not understanding, perhaps? Okay.
You gotta read between the lines. They don't mean it.
Yeah, and just in case, here we have, let's get Mr. Feynman to testify for himself. He's dead too, but he left his testimony. Here it is, okay? Says, is it true that the particle, he says this in lecture number 19 of his Feynman lectures, and it's titled The Principle of Least Action, where he actually explains, the path integral. And he gave these between 61 and 64. He says, is it true that the particle doesn't just take the right path, but that it looks at all the other possible trajectories? The miracle of it all is, of course, that it does just that. That's his words. They take all possible paths. He says that's what the laws of quantum mechanics say. Okay, so these are the laws of quantum mechanics. It's not like I'm inventing anything here. Okay, it isn't that a particle takes the path of least action, but that it smells all the paths in the neighborhood and chooses the one that has the least action. So we have particles choosing. They have this intelligence. Okay. Well, you can read the rest of it there later, but that's the point. The point is that, yes, I know it sounds ridiculous, it sounds irrational, it sounds uncommonsensical. And,
nonsensical.
Yeah. And what all these people are telling you is, yes, from A to B, quantum, not classical mechanics, but quantum mechanics proposes that a particle takes all imaginable paths. And it's not that it can. It's that it does indeed take all these paths because the particle is everywhere at once, according to quantum mechanics. Where did they get that? They got that from the uncertainty principle, Heisenberg's principle of indeterminacy. And it says that a particle essentially behaves like a wave. Suddenly, when you're not looking, you don't have to look. You don't have to peek because that's cheating. Okay, and so what he says, if you're not looking, the particle is everywhere. And only it condenses to a point when you look and touch and measure it. Then boom, suddenly there's the wave function collapse.
It knows it's being watched.
Yeah, it doesn't like to be watched. Maybe it's nude and covers itself real quick, and then it goes again as a wave. So yeah, that's what quantum mechanics is saying. So if you think that's rational, well, that's up to you to determine. Personally, I can give you my opinion. I think it's nonsense, okay? But that's the only explanation they have because they have this uncertainty principle and they have the principle of complementarity that particle is a wave and wave is a particle, and they have the, exclusion principle. They have all these principles which form the foundations of quantum mechanics. Now you're going to challenge that after 100 years of quantum? Come on. Okay, another fellow asked a different kind of question here, and he said...
is it a question or is he just going to shit on you? But
Yeah.
I feel like most of these are 90% just...
we bring these guys just so we learn. We learn what the arguments are, okay? He says, what a bunch of gobbledygooky this talk. A field is a bunch of numbers? Cannot exert forces? Because that's what I'm saying. I'm saying, a field cannot exert forces, and it is a bunch of numbers. And this guy's questioning that. Said, what the hell are you talking about? Everyone knows and testifies that the electric field, whatever the name you do for this, exerts force on any type of matter independent of its type. So the magnetic field is also a concept? Yeah. The force you feel gushing, pushing, and pulling your hands is also fantasy? Yeah, because force is not a physical object, so that's why. I think you need to review your basic philosophy.
Ooh.
Laughing out loud. Okay, let's find out what
philosophy word.
Let's find out what the answer to that is. Okay, here we have it. And it goes something like this. We look up the word field so we know what we're talking about. And this is out of the Wikipedia. It says, a quantity. What is a field? A quantity.
We're already off to the wrong start. That's just numbers.
So I was saying that he says, what is a bunch of numbers? Yeah, that's what it is. Field, a quantity represented by a number that has a value for each point in space and time.
A graph, essentially.
Yeah, it's a bunch of numbers like you see on the bottom left there.
But isn't that essentially used as a graph? Fields?
What do you mean, graph?
Aren't all fields essentially used as a graph? Like they take two, they use x's and y's to kind of say this is this many units away from that.
Yeah. Essentially that is, but what the field is the composite of all of them. It's not just one point. A field is what it says. It has a value for each point in space and time. In other words, the field is the whole works. It's not just one value. That's only a component of the field. The field is the whole thing. In other words, if you have a gravitational field, you look at how strong it is near the center of gravity. So you have the Earth. Let's assume it's perfectly round. Let's assume the center of gravity is the center of the Earth. Okay, that gravitational field extends beyond the borders
of the
object, which is the Earth. And what are we talking about? Well, we're talking about values of gravitational potential or strength the farther away you get from the Earth. Same with electric field, same with magnetic field.
But that's essentially used to map.
Yeah, exactly. That's what it is.
It's not actually the map isn't the territory.
Yeah, but the point here is the word field refers to that map.
Yeah.
To the volume of numbers of units, of quantities, of amounts that surround an object. So they're referring to the amounts because it's a mathematical concept. We have to understand that. And but here's the problem. Here's the little trick. This is how it's done. And this is also out of the same source. Wikipedia says a field occupies space. What do you mean occupies? How does a quantity, a number, a value, how does that occupy space? Suddenly they morphed the quantity, number, value, amount, whatever you want to call it. They turned it into a physical object, like you see on the bottom. They took all those numbers and turned it into a rock.
They're saying length is an object. It takes up room.
What they're saying is essentially that these bunch of numbers suddenly converted into something that takes up space. It says contains energy, and its presence precludes a classical true vacuum, meaning you don't have vacuum there anymore. Now you have something that's interrupting the vacuum. And he said, listen to this next statement. It says, this has led physicists to consider electromagnetic fields to be a physical entity.
So something we invented to map an area is now an object.
And just in case, the word entity, you look it up, something that has real existence, a thing. What are the synonyms? Body, material, matter, organism, substance, thing, something. So yeah, they converted this number, they converted into a thing. And this is where the danger comes in. That's a quick magic trick that they did right there. They said, we're going to convert this into a thing because we need to relate what we're talking about to physics. Because otherwise it would be just pure mathematics. Nobody would care. But they say, no. Yeah, listen to us. These numbers here that are around there, they occupy space.
They have to translate it into some
into
form of pseudo-physics.
Tangible, seeable.
Yeah, just so it has some bearing on reality. If it's just all numbers, then it's not going anywhere.
So here's a field for you. If you want to see a field, here it is, okay? That's a field. And it's a magnetic field. And you see the magnet, that's a physical object, okay? But now we're going to remove the magnet, and what are we going to leave? We're going to leave the field only. Is there such a thing as a standalone field? I mean, is that an object?
Well, to clarify, I think the original post, the original question there,
Yeah.
I think that person, as well as many others, confused the effects
Right.
that are around a so-called field with the field, like as if it's they're confusing the numbers of amounts with the effects that we see.
But that's why we have to define these terms. We have to know what the word field means or refers to. You can't just say, well, we use a field every day. Like, here's a field. We have two magnets, okay, those two black ones there, and you have a magnetic field. Something is in there.
Yeah, something is.
And so they call that something that takes up space or that whatever. They define it as a bunch of numbers, but then they say now they're going to treat it as a physical thing. They say there's a field in there, a magnetic field.
That's
Hold
what
it. But you made a jump from mathematics into physics without any justification. You turn this definition, which is a whole bunch of numbers, and you turn that into a physical object. And you say, well, there's an object there.
They jump between the two as if there were no barriers.
Right. And this is where the danger comes in. And again, that's why I remove the magnet and say, is there a standalone field? Is there a physical object there that just stands alone? And of course, a lot of people at least would say, no, there's no such monster. You can't bring the field into the conference room. You need to bring the magnets. Okay, otherwise the field stays behind. Okay, and so here's what a field really is. And here you have all different kinds of fields. You have magnetic, you have gravitational, etc., electric, and here it is. Here's what they are.
That's
okay?
trippy.
What are these? These are all vectors. That's what they are. Because a field is modeled with vectors. What are vectors? They're number lines. They have magnitude and direction. And what you see, this is what you're seeing, okay? What they've done is take these vectors and put them in motion. These are mathematical concepts, which are numbers that have direction, right? If you can imagine that. And they define it as such, but then they put them into motion. They represent them with a little arrow, Indian arrow, and they start moving them around. And so you say, well, I understand what that is. There's this field moving. No, there's no field moving. What you're staring at is a bunch of mathematical vectors, number lines, magnitude and direction that suddenly that are represented by arrows, and they start moving them around. You say, well, yeah, that occupies space, obviously. But what you're staring at is numbers.
You're saying there's a 3 pointing north, and they're moving the 3 pointing north.
Exactly.
What does that even mean?
It has no meaning. But see, they had to have a physical interpretation to their mathematical description or equations or... so what their numbers, their definitions. So they have all these numbers, vectors, magnitude and direction. They represent it with an arrow, and you say, okay, I know what an arrow is. That's what the Indian killed the soldier with, right? Yeah. And so they put a little arrow there, and they say, okay, that's a physical object. Then they put many of these arrows, because what is a field? A field is a bunch of numbers from a given point, and here we have a bunch of arrows, a bunch of numbered lines from a point represented by an arrow. And then they put them into motion, which is very scary, because now the number lines are moving. It's very scary stuff.
Does that mean the arrow, the magnitude has magnitude because they're moving an arrow? It's already a number with direction, but then if you move it this way, that means it has its own.
Yeah, they change the direction of the arrow because what happens is for any given point, they show how it moves. Okay, and they represent that motion, what is called a translation or a transformation in mathematics. What they do is they start moving these arrows, these number lines around. Very scary stuff. But when you have a whole bunch of them, because again, a field is a whole bunch of these numbers, well, then you have all this motion. You say, well, yeah, I understand that. Yeah, I see why it occupies space. And you're staring at number lines being represented by arrows because they had to put some physical thing there to represent their equations, their numbers, their definitions. This is where the danger is when you turn that mathematics into physics with no justification, no way to to back that up with. Okay, and so under the rope model, we like to always point that out. Here it is. Are we talking about a physical entity representing a magnetic field? Yes, here it is, okay? So if I can put it up there, there it is.
Oh, we're doing actual physics.
Yeah, and so now you see they're threads. Under the rope model, what we have are threads, and those threads, those moving threads represent, or not represent, they're actually the field, the so-called
You don't
field.
have to use the word represent
Yeah, here
anymore.
you don't need to represent.
Imagine it like that. No, it is.
Yeah, it is. What you have here is that the so-called field is mediated by threads that are moving around. And I don't have it here today, but in general, I've shown that a magnetic field, if you put a magnet underwater, it collects one iron filing at a time because there's something sweeping. The so-called field, static field, there's no such monster. Field is made of something that is in motion, or like James Maxwell said, there's matter in motion.
It's not
in the field.
It's not instant.
Right, it's not instant. You under the water, because you can see it in slow motion. Essentially, when the magnet's underwater, you can see the magnetic field, whatever that is, pulling one iron filing at a time. What do you have under the rope model? You have the threads moving around, and they're picking up these iron filings and putting them against the magnet itself. So we do have a physical object representing the field or mediating, simulating the field. They don't. What they have is number lines, which they arbitrarily put an arrow there. What's an arrow? It's a vector. And then they start moving the vectors because they're not interested in what really is in that invisible, intangible region. What they want to do is just map it with number lines.
They just gave the motions and forces names, but they didn't say what spurs them on, what does that.
And so you cannot visualize their mechanism because they're representing them with numbers, and they cheat and they say, well, that's really an arrow. It's not an arrow. You're staring at a number line, magnitude and direction. And as long as you keep that in mind, don't lose sight of that, you'll see that you will have no physical interpretation for what a magnet is or how it works or what a field is. They define it again as a concept, abstract concept, a bunch of numbers, and then they turn it into a rock. Okay, another issue that was raised, and several people had questions on this, so I'm just going to put one of them, okay, and we're going to address the main one, the first fellow who put this in there. Okay, it's got to do with the thread. Okay, fellow says the thread doesn't exist according to your definition of the term exist, which you see at the bottom. What does exist? Physical presence. In order to define the word exist, you need an object, and the object must have location. Okay,
that's good.
so if God wants to exist, it's not enough that he's an object, like a magician. He's got to have location. There's got to be distance between my chest and his. Otherwise, God doesn't exist by definition. Because we do have a definition of exist now, and that's what he's referring to. He's saying, well, if there's a single thread out there, one thread in the universe, right? Well, what is it in relation to? What is this thread located with respect to if it's a single thread in the universe? That was his concern, okay?
That's a good question.
One person answered all that. He says, please explain. Okay, and one guy took the first words out of my mouth, and he says, yes, the thread doesn't exist according to my definition of exist. What do you need explained? And he took that first part out of my mouth. He beat me to it. Okay, fine. But this guy continued, and he comes back and says, no thread. He's trying to explain why. He wants an explanation. He says, no thread, no rope, no hypothesis. In other words, if you cannot say that the thread exists, then your whole theory goes down the drain because the thread you're talking about, according to your own definition, doesn't exist. That's his argument. Okay, let's find out how we answer this. Very simple. Okay. Let's make it exist. He wants the thread to exist. Let's make it exist. Okay, here it is. Okay, we're going to make it exist. If I can get this thing up there. They're all at the bottom, so it takes
We're not going to use the instant on, are we?
Okay, here it is. Okay, so now it exists. We have two threads, right? And one thread exists with respect to the other thread. Okay, they have location, they have distance with respect to each other. There's two of them. Okay, and remember what this represents. These represent two universes. Remember, the thread really turns into this. Okay, where you have these two universes. They're all tied together. In other words, the thread turns into atoms, which turn into ropes, which turn into atoms, and eventually into stars, galaxies, whatever. Okay, and now you're going to say, well, Bill, you cheated. You cheated because you put an extra thread in there. I thought it was a single thread.
Yeah.
So I'm a cheater.
You are a cheater. I'm on this guy's side.
Okay, so he says the thread doesn't exist because you have a single thread. Well, I put another thread. What's wrong with that? I mean, it's speculation, right? You say, well, how do you know it exists? Well, it exists by definition because now we have two threads. That's why. Remember, whether there's a first thread or a single thread, or in other words, the single thread refers to our universe. And it could be another single
Oh, we got the multiverse.
Oh, yeah,
the multiverse
exactly,
on deck.
Exactly. You want 100 threads? We'll put 100 threads in there, okay? We have space, right? And we have these threads, and one thread is located with respect to another thread, with respect to another thread, and so on down the line. So what's wrong with that? Now we have the existence of the thread. You wanted existence, I gave you existence. But let me tell you what the real problem is. Let's get to the bottom of this, okay? That's just word wizardry I just gave you, okay? I'm just putting another thread there to show you that, yeah, it can exist. All you have to do is put another thread. Now you have one thread, with respect to another thread, right? Yeah. And you say you're a cheater, Bill. You put another thread by proxy there. You just did it to win the conversation. That's unfair. You just wanted to win the debate, and so you said, "See, now it exists." Well, it does exist because that's the definition of exist. What's the issue? This is the issue. Let's get down to the rock bottom to what the issues are. There's several issues. Let me bring this up. I'm going to cover your face.
Go ahead.
Okay, here are the issues. Okay. I didn't call it the thread hypothesis. I called it the rope hypothesis. Why? Because the thread is irrelevant. We do absolutely nothing with a single thread. Let me repeat that. We do absolutely nothing in physics with a single thread unless you're talking about another thread, another universe. Then we can do something with the thread, talk about the universe as a whole. In other words, treat the thread as an object that has location with respect to another object because they're not bound to each other in any way. So there is distance, there is separation, we're done. Okay? So the only time you're going to use the single thread is if there is another single thread out there. Otherwise, you have no use for the single thread. We have no use for the single thread in physics. What are the issues in physics? Well, the thread is, again, it's not an issue in physics any more than a parallel universe is an issue in physics. These are speculations. We say, well, what if there were another universe? Well, then you get into a chat by the water cooler and talk about that. But that doesn't concern us. What are we concerned with? We're concerned in physics with visible and invisible phenomena. The visible ones, we figured them all out a long time ago. Okay, we can see the seesaw, we can see the rock going through the window, we can see the pulley pulling on something. We see these things. All those are done. The ones we have not figured out are the ones you see there. Light, gravity, magnetism, electricity, and the atom. Those are invisible, intangible, and that's where we're having problems because people are not used to representing those or mediating them or simulating them with physical objects because we can't see and touch them, and we always thought that an object is that which you can see and touch. And we're saying, no, it's that which has shape, and now we have a different notion of what these things are. They're mediated by things that have shape. Okay, but what is the issue here? These phenomena are mediated by atoms and ropes, okay? And so we get to a little point that we find out that the thread is the only object in the universe because everything else is connected, as you see below. And let me give you here an example so that you see where I'm going with this, okay?
A little higher.
Did you get it up here?
Yeah, there's one more. No.
I lost it. Ah!
So at the top.
Where'd it go?
It's not showing up. Oh, you have to click the eye.
Oh, that's what it is. Okay, Jesus. Good thing you saw that. Okay, so we have the rock and we have a table. But it turns out that the only reason we can treat the rock different from the table is that we can't see the ropes. So we say, well, the rock is a discrete entity and so is the table. But under the rope model, if every atom from the rock is connected to every atom of the table, well, then the rock continues and becomes the table, and the table continues and becomes the rock. There is no difference between these two objects. The only real object in the universe is the single thread, right? That's according to the rope model. Everything's connected. But are we saying that we're not going to talk about rocks, we're not going to talk about tables because everything in the universe is connected and everything is mediated by a single thread, the single thread in the universe? We're here trying to do physics, and physics deals with light, gravity, etc., okay, magnetism. And so we're going to talk about objects, and we're going to treat them as if, as if they have a border, a surface. We're not going to include the ropes when we talk about rock or table. We have to treat them as discrete objects. They end where the visible or tangible part ends, which is the last atom. And then from there, the rope that continues, we're not going to consider that part of the rock because the rope is going to go to the table and going to go to the house and going to go to the dog and so on.
You're saying for the questions we want answered, we don't need the thread.
We don't need the thread at all. The only time we need the thread, and that's what I'm going to show next, okay, this is when we need the thread, okay, and it's only locally, okay, that's when we talk about the thread. And here's one example, okay, which I just showed a minute ago. Now we need the thread because we have to explain how how magnets attract other magnets by way of the thread, by simulating the field with a thread. But now we're talking about the local action of the thread. We're not talking about the single thread that underlies all matter. We have no use for the single thread. We only have use for the thread locally. And here's another example, okay, which are I think the only two instances where we use the single thread, okay, and it's how the
electron shell.
The electron shell is built. Okay, let me get this one out here. Okay, this time you get to see you. So the atom is weaved. The surface of the atom is weaved by countless threads coming from every rope in the universe that converges on our atom. And so those are the only time we talk about the thread. So the thread weaves and constructs the atom. It constructs not only the proton dandelion, which is just a bunch of threads. Okay, it also constructs the electron shell that encapsulates the proton dandelion, as we call it, or you can call it the urchin. Anyway, you want a star, any word will do, find any description. And that's the only time you talk about the thread, because the thread locally can be used to explain these things. But the global thread, the one that underlies all matter, we have no use for it, except when we're talking about another universe, and I just showed that when we put another universe out there, then the threads exist, both of them. Okay? So that's the issue. The issue is that people who harp on the word thread are just people who lost their religion, and they can't win the game, they can't beat them, so they want to tie them.
Or this is a confirmation of multiverses.
No, because again, that's speculation. You can speculate about that, but again, that goes to the water cooler. That has real little to do with actual physics. You're not going to explain anything in physics like magnetism here or gravity or anything like that by talking about the single thread existing with respect to another thread that could be out there. That's for speculation. That's good to talk about, but it doesn't pertain specifically to physics.
Yeah, but all physics is water cooler talk.
No, I got to explain the mechanism. I got to explain this mechanism.
That's still water cooler talk, isn't it?
No, it's not.
What's the difference?
No, this one I got to explain the mechanism, and all I'm saying here is that.
Well, there's no mechanisms.
Well, no. This is the issue. The issue is that I'm going to explain to you an objective mechanism so that you understand it. You say, this is what I propose that's happening between these two magnets. The threads move around. This is how they attract. This is how they repel. That's it. Whether you believe that there are threads, whether you believe in the theory, that's your personal issue. But my point is that physics is about explaining a mechanism. I explain the mechanism, I'm done. That's what I need the thread for. But when you're talking about something like the global thread, assuming there's only one in the universe, there's no purpose in talking about the thread itself. I'm not going to use that for anything. And if you say, well, does it exist? Well, it exists if we have another universe out there, another thread out there. And because what are you going to use that thread for? Only in reference to another thread in the multi-universe. Otherwise, you have no reason to raise the issue of the single thread existing or not.
Well, you would with itself, I guess.
Yeah, but all you're doing is defining the word exist. That's your issue. And if you want to talk about the word exist, I'll make it exist immediately. I'll make another thread, and now the thread exists. These are single threads, many single threads. Each one is a universe. So we're talking about the word exist, not about the thread. And it's very easy to make the thread exist. Like, it's easy to make God exist. Just make another God.
Do we need the thread to exist? That's a separate
that's the point. We don't unless we're talking about another thread. Then we need it.
Do we need the word exist for the thread?
That's what I'm saying. If you're going to talk about the thread, talk about the thread. If you're going to talk about exist, we make it exist immediately. We make another thread. Very simple. I do it with my magic wand. Cheating. That's how I do it. Okay, another issue, moving on here.
Real quick before we go on,
Yeah.
would that mean that could location be changed to things along the thread then? Not the thread itself, but basically when you're talking about a table and a ball, you're talking about two different chunks of the thread.
Yeah, and that's essentially it. When we talk about exist, we usually talk about anything made out of atoms. Okay, so we say the table exists, the one that I'm touching, the one that I see. Even the air that you can't see, you say, well, it exists because I can move my hand and there's something there, I'll call that air. And it's made out of atoms, or at least it's proposed that it's made out of atoms. Any gas, for that matter, water is also made out of atoms. So we talk about things that exist as being made of atoms in the real world. We don't talk about exist in terms of energy, meaning the mediator of light. Okay, we don't say, does light exist? Well, light exists, in the sense that I shine it on the wall and I see something there, and in that sense it exists. When you say, well, does the energy that supposedly mediates that, what is that? Well, that's a concept, and so you get into this runaround. Now, when we use the word exist, we usually refer to atoms locally. We talk about the chair, we talk about the table, we talk about the dog, the house, and so we talk about things of that nature, and that's the context of the word exist. And what we're saying is, when you're going to use that word exist, which is physics is the science of existence, then what you have to do is apply it locally and say, well, does the table exist? Well, yes, it does. Well, what do you mean by that? Well, all we're saying is it has locations. An object that has location.
I think the problem with definitions usually arises when we're talking about definitions without an actual presentation. No one's giving a presentation. We're just defining words for the sake of defining words. No one's giving a presentation. So you can't really define a word in a vacuum because it has no use. It's not being applied. So you can't really see where it's falling apart. You are when you're saying a theory. In other words, if people say, well, love exists, and they just say that, well, yeah, you can use that in poetry. But if you're going to talk about, hey, God exists, I can prove it, and here's my evidence, or what, now you walk the line into physics, and now you got to talk rationally. Now you have to define the word exists very specifically because we need to understand what you're saying. But if you just say, the mountain exists and in ordinary speech, or love exists, or intelligence exists, well, we don't know what you're talking about. It doesn't matter. You don't have to be specific because it's okay. Ordinary speech does not require very rigid definitions, okay? Rigorous, etc. If you're going to make a theory, if you're going to talk even at the water cooler about a theory, whether you know it or not, you've crossed the line into physics. Now you better be rational. And if you're going to be rational, the first thing, define your terms. Especially the words like object and exist. Those two need to be defined because you're going to talk to me about what's real out there. You're going to say, well, I saw the ghost. Well, does the ghost exist? Well, yes, I know it exists because I can touch it.
Well, is that the definition of exist? If you're going to talk if you're going to talk seriously, right, then you better define your terms. Otherwise, you can say whatever you want. Okay.
Then you can say love touched me.
Yeah, because you got to try to you have to try to understand what the person is saying. If the guy's just going to use ordinary speech and not define his terms, well, he's just going to be chasing his tail, and you're going to go around in circles because you don't understand what he's saying. You have to pinpoint the problem, and that's definitions. You got to say, what did you mean by object? What did you mean by exist? And that's where the trouble comes in, because people are not used to defining these terms, not in a rigorous manner. Okay. Okay, let's move on. Here's another issue. The person says the ether. Okay, it says
the old ether.
He says ether is the name of the black stuff. Oh, it is an object, the black stuff. Okay, but it doesn't exist because it goes to infinity and therefore has no location. Okay, again, he's using the same definition. We just use object plus location. It is synonymous with space and the thread.
Which thread is he talking
Well,
about?
he's talking about the single thread. No, and let's find out why. Okay, we got a problem with this. Several problems. Okay, so let's clarify each one of these problems. Here's the first one, or several at the same time. There we go. Okay, here's the ether, and you can see that when we talk about the ether, we talk about light, because what these people are saying is that the ether mediates light. It's the vibration of the ether that's what light is, the vibration of the ether. And so you can't say that the white stuff is, that the black stuff is the ether. No, it's the white stuff. For otherwise, what is the white stuff? Tell me what the white stuff is then. If the black stuff is the ether, what's the white stuff? And then again, they always say that light is the waving of the ether. And what's that? A bunch of particles. That's what the ether has always been. They just say that that's this sandbox or beehive, all these bees moving around up and down for some reason in a coordinated way where they have these sine waves. And so, yeah, okay, so it's the particles. They're talking about the particles moving up and down and creating these waves. So, yeah, the ether is a bunch of particles. That's what it's always been. If you have a different definition, you have to define the word ether and tell us exactly what you mean by that. And hopefully you cannot define the word ether, because if you do define the word ether, it's not an object. Objects we don't define, objects we point to. It is concepts that we define. Then the black stuff cannot be infinite, because if it is, it's not an object. We have no objects that are infinite. So again, if this fellow says that it goes to infinity, but it's an object, no way. Black stuff cannot go to infinity because otherwise, if it's infinite, it defeats the definition of object, which is finite. And if it's finite, you got to tell me what's on the outside of it, limiting the black stuff. What's on the outside of the black stuff? So either way, you got a problem, and you got to define the term so we know what you're talking about. And then finally, the thread is not the ether, it's not the nothing, it's not the black stuff. As you can see, the thread, the single thread at least that we propose, underlies all matter, is an object. It has beginning and an end. It's a closed loop thread. Okay, so that's different than the ether that you see on the left or on the upper right there. Okay, so no, the thread is not the same thing as the black stuff, and it's not synonymous with space. Space is the black stuff. Thread is the red stuff. Okay, so let's get. We need to define these terms so that we can all talk in a way that we comprehend. You don't like the definitions? No problem. I have no problem with that. But then you have to, you can't say, Bill, you're wrong. That's not the ether, which is what every etherist does. He says, that's not the ether. Like this guy said in quantum, he says, that's not what quantum says, that a particle goes through all these regions.
Well, you could be mistaken, but then what is the ether?
Right. Don't tell me what ain't. Tell me what is.
Well, tell me both. If it ain't,
oh, yeah,
what is.
It's fine. They can say, Bill, you're wrong. You don't know what you're talking about.
That's not what I meant.
Fine.
That's not what I meant.
Fine. Then you got to tell me what
But that's
is.
where the problem arises, because there's many different notions of the ether, and when you attack one, you attack ether A, ether B says, oh, that's not mine, though. You attack ether B, ether C comes out and says, oh, that's not what I meant.
And and that's happened because all these people come in and say what the ether ain't. Everybody knows what it ain't, and it's whatever I say that's not it. And I say it's a bunch of particles. Okay, fine, I'm wrong. Great, I'll concede. Tell me what is. Don't tell me what ain't.
Sounds like the Tao. They always define it what it isn't.
Yeah, and this is the problem. The problem is anyone who's an etherist, the thing you'll never see them do is define the word ether. And again, he better not be able to define the word ether, because if he does, it's a concept, not an object. Objects we point to. And if it's a bunch of particles, it's a concept, because I say, which one is the ether? Which of those white particles is the ether? You say, no, the whole thing is. Well, that's mereology. Bunch of particles is not a physical object, any more than table is a bunch of particles, or an elephant is a bunch of particles. No, an elephant's what I pointed to. So when I point to the bunch of particles moving there, what's the ether? Which one is the ether? And you say the whole thing. No, that's not an object. That's what it's made of. I need to see, does the whole ether move when you're talking about light? You're saying the ether vibrates and that's light? Well, what, the whole universe is vibrating? Is that what you're saying? You're moving around as a whole? I can move an elephant as a whole, but to say that the ether is one of the atoms inside the elephant that's moving up and down, that's a different story, because that's not an elephant. That's an atom. And that's the same issue here. If you're going to talk about the ether, you're talking about the whole shebang. Okay, and then it's got to be made of a single piece for the purposes of physics. You point and name, say that's the ether. If you're going to say that ether is all these little particles that are moving around, then that's not a physical object. That's a concept. That's mereology. That's what the ether is made of.
Can you bring up the picture again?
Which one?
The one you just had?
Well, I had two of them. Here's one.
That one.
Okay.
I got a question. What's the black stuff around the thread?
It's space. Nothing.
There you go.
It's nothing. You're looking at nothing. What's that stuff between the moon and the earth that you see every night? It's called nothing. And you say, well, there's something in there. Between somethings, we have nothing. So make it as small as you want. On the moon, there's 10 to the minus 11 torr vacuum. That means there's one particle every so often per volume. What's the rest of the volume? I want to know, someone to tell me what the rest of the volume is. It's called space. That's what gives contrast to that little particle, to that atom that the detector, the ion gauge or whatever detected. Okay, moving on here. Two more issues. One file says, the same thing can be nothing and something, depending on how you are looking at it. Okay, I'll look at it upside down. I guess something becomes nothing. Okay, the hole in the database where this comment was inserted, he's talking about, what happens inside a chip, for example, that you have atoms in there, and the chip is in your computer. And so he's talking about this, okay, that's the context. He says the hole in the database where this comment was inserted was nothing in the context of memory. But the storage units the memory exists on is something in the context of our world. He's saying, in other words, when you store a bit or a byte or whatever, right? Let's talk about a bit, which is the smallest unit of memory, you could say, okay? He's saying when you store it, what are you storing? You're storing nothing, but it becomes something, that exists in memory. Why does he get into this chasing his tail thing in this circular argument? Because he doesn't define his terms. That's where the problem starts.
That seems to always be the only problem.
Yeah, we have a language problem, not a question of physics. First we got to solve the question of language.
We got an English problem.
Yeah, we have an English problem. What is it? What is it called? Semantic problem. First we define. So what is something? We say that which has shape. What is nothing? That which doesn't have shape. Now we can use these words consistently. Why? Because they are antonyms. Something is an antonym. Yeah, so this is what we're proposing. You don't like this? No problem. Define something and nothing. Then we can follow your train of thought. And here we have the word exist. Okay, again, object plus location. Something that has location. Okay, so that's our starting point so that we can use these words consistently in a dissertation, in a talk. And so this is more or less what this fellow is referring to. I talked about that the other day. Here you have the depletion region of two semiconductor crystals. You put them together and you create this region where the extra electron from one atom jumps over, according to quantum, to the hole that is in the other side of in this case, the p crystal structure, and creates this depletion region. Okay, so that's essentially how semiconductors, in this case a diode, are put together. You have a p-type, usually boron, an n-type, usually phosphorus. When you put them together, okay, immediately, as soon as they're touching one with the other, you create this depletion region. And the theory is that the extra electron of the n-type jumps over to the hole. There's a missing electron in the p-type crystal. Okay, so that's essentially, and it creates this depletion region, which is very useful for diodes and transistors. Okay, so that's the starting point. Okay, now let's get this other thing here. This is what I showed the other day. And what do we have here? Well, what we have here again is holes, absence of electrons, okay? Positive absence of electrons moving to the negative pole, to the cathode. Okay, that's essentially what we have. And
this is according to them.
Yeah, this is according to quantum mechanics. So the question here is, what object are we talking about? Does that hole have shape? Well, if you take the rest of it away, because the absence of an electron is not a physical object. That sounds like like a word wizardry. We're saying that if you see the absence of an electron bead, we're going to call that a hole. And again, that's like, again, you're moving holes here. What are you moving? It's like I showed the other day, the game of the puzzle,
close to the camera.
Yeah, where if you move this over to here, the hole is moving in the opposite direction. So if the little square here is the electron, the hole, the absence of an electron, that's what's moving in the opposite direction. And they call that, are you going to call that an object? Does that have shape in the absence of an electron? I mean, what is a whole?
Yeah, you can't really remove the rest of it and just leave a hole.
And much dangerous is to say that the whole is positive. A positive whole. I mean, we can all more or less try to figure out an electron being negative is okay, negative electron, whatever negative means, but a positive nothing? I don't know.
I'm sure it's been asked before, but holes have shape. Are they?
Yeah, but as soon as you take the ground away from Bugs Bunny's hole, there is, what do you have? I mean, what is a hole in space? Which is what a black hole is. Black hole is a hole in space. If space is nothing, what is the hole through? What is a wormhole through going to another universe? You drill through what?
Yeah.
So we have all these problems. You have to define your terms of something and nothing before we can talk rationally and not chase our tails around. That's the issue. You got to get down to language. Okay, that's where physics starts. That's where science starts. At language.
I guess hole isn't an object because hole is space.
It's the absence of an object.
Well, yeah, no, but that's not the issue because if you have a hole, you can have a circular hole, or let's say not circular because that's too
Bugs Bunny hole.
Speaking 3D, let's say cylinder-shaped hole in the ground, right? So we have a shape, but that's not an object because the hole. It's not that it's not made of atoms. It's that it's just an extension of space. It's an extension of nothingness, which has no
shape.
Yeah, there is no shape because it's just an extension of space. So weirdly enough, a hole can have shape in regular speech, but in physics, it's not an object because it doesn't actually have a shape because the end of that hole it's not a 3D shape.
Right.
Because
and you just said it that the issue in ordinary speech is that the word whole is a noun. That's where the problem
No,
is.
that's not the problem. The
but
problem
that is part of the problem because you treat it as a subject of a sentence. You talk about the whole.
No, but that's not what I'm saying. I'm saying a hole has a shape. When we look at a hole, we see a cylinder hole.
Also,
but that's not the end of the cylinder. The cylinder keeps going off into the rest of space, which doesn't have a boundary, so it doesn't actually have an end of shape.
One of the arguments I make in relation to that, I work with vacuum chambers, and let's assume perfect vacuum. Okay, so we have this chamber, cubic chamber, 1 meter cube chamber. Okay. You're going to vacuum, you're going to create a vacuum in that chamber. You're going to suck all the air, all the water, all the atoms from that chamber. Nothing in there. Let's assume perfect vacuum. Let's say we could achieve that. Okay, now you have your vacuum chamber here on Earth, right? But the Earth is moving around the universe, around the solar system for sure, right?
Are you taking the hole with you?
Are you taking the hole with you? Or are you creating new holes as you move along?
I guess that goes to the point.
The merry-go-round.
But I think that goes to the point that whenever you say there's always space between two objects, that's essentially what you're talking about.
No.
Because because there's always there's no such thing as an encapsulated hole, right? Is that true or not? There's no such thing as an.
And I forgot to mention that earlier, and that's why I'm going to close his mouth. Remember that between any two atoms, there's a rope. And that means that under the rope model, okay, distance is the length of a rope.
Yeah.
So we have to have a new definition for distance, or a new notion. We have to make sure, like, we can have distance between two ropes because there is no rope between uniting or connecting two ropes. But between two atoms, which is what we talk about when we talk about existence and about objects, we have a rope, but remember the rope continues to an atom, which continues to a rope, which continues to an atom, and so on down the line. So there is no discrete object. So when we have two atoms, it doesn't matter what they belong to. One belongs to a chair, the other one belongs to a table. We say, well, the distance between the table and the chair is, 3 meters. And you say, well, what is between that? And because there's gravitational attraction, even though we can't really measure it at that level, but we know that there's gravitational attraction between the chair and the table because of the Cavendish experiment. And the question is, what's in between there? Well, under the rope model, we have a rope. And so distance becomes the length of the rope. There is no empty space. So I just wanted to correct that there to clarify that point.
We're on deep.
Oh, yeah, rabbit hole.
We got a lot of questions lined up. So.
Okay, so last question here. See if we can get this. This is down the line of my son here who loves this stuff. Guy goes in there and looks at Ayn Rand, which I covered in the past, and he says, then what is philosophy then in the alternative? Because I'm saying that Ayn Rand was not a philosopher, okay? Okay, so what is philosophy in the alternative under the rope model? And very quickly, here it is. Okay, here we have to define these terms again so that we know what we're talking about. And so here's a summary, and I'll go quickly through this. We have science is divided into physics and philosophy. Physics deals with causes and mechanisms, and philosophy with reasons and purpose. And what is the purpose of physics? Rational explanations of phenomena, of things that happen. And philosophy is the rational explanation of behaviors. What is religion? Well, it's subjective. It's just opinions and beliefs. Okay, it's what you think is truth to you. Essentially, it's personal. And what are irrational explanations that you see over on the right? Well, that's when you start moving concepts around and when you treat concepts as physical objects. That's the primary one. It's known as reification. And here is a definition of that, so very quickly.
Your definition, or?
Yeah, this is our definition of the word irrational. These are the criteria for irrationality, and the main ones there are reifying concepts, turning them into physical objects, which is what this fellow did with field. He turned it into a physical object. He turned these numbers into a rock. Others is no definitions or using them inconsistently. Theory doesn't follow from the hypothesis, etc., etc., etc. Okay, we'll open up the floor now for questions if you're still around. Okay, so
Put these next to each other.
okay, my son stole my mouse from me
We
now.
got a long list. Okay, here we go.
Okay, let's go with it.
I'm gonna farm out the questions. Any takes on Kantian philosophy?
Well, Kant, again, the issue I've got with Kant primarily is with respect to physics, and I guess there's primarily two issues there. One is his notion of object was no different than his predecessor, David Hume, okay? And that's that they could not distinguish, like anyone after them, between what an object is and what an exist is. The other one I have with Kant is his notion of galaxy, okay? He's essentially the guy who probably is one of the first persons to realize that there's something called a galaxy, these island universes out there. And so he gets 100 points for that. Again, probably the first one. I don't know if he was the first one, but I know he talked about it in his writings. And so I credit him as the first one unless someone corrects me, okay? That's it. That's all I've got to say about Kant. Other than that, he's not a philosopher. He's not a philosopher, again, under my notion or my definition of philosophy, because philosophy is not opinion, recommendation, which is what Kant did. Philosophy is explanation of behavior, which is what Kant essentially did not do. And nobody else after or before him. From Aristotle all the way to Ayn Rand and Jean-Paul Sartre, all these people did the same thing. They did opinions and recommendations. I don't consider that philosophy.
Sometimes some of these questions are asked in context to something that we're speaking about in the moment, and the context kind of falls away when the question is asked later.
Yeah.
So some of those I kind of have to skip.
All we can do is answer as best as we can, and then
If at all
when someone
possible.
comes later and say, "Bill, but you didn't answer my question," or
Yeah.
"I didn't understand it," or "You took it out of context," or whatever, okay, fine. We need to clarify these things. All I can do is tell you how I look at these things, and the way I look at them. First, we define philosophy, and philosophy is not what Kant did. And
No, I'm not talking about the Kant one.
well, I'm just in general. I'm just saying we have a different notion of philosophy in this channel, and because there is a different notion, you have to be careful when you talk about the word philosophy. Okay.
The next question I think we already answered, but let's ask it again. What is the black in between when you draw double ropes, single thread?
Double rope. What do you mean? Double threads? You mean?
I
Probably a rope. Well,
Double threads, single.
well,
What
keep
is the
in mind.
black still?
Here's a rope. Okay, here's a rope. And why do we distinguish the blue from the red? Well, hopefully there's something separating the blue and the red. The blue and the red do not merge and become one. Okay, so there is something, not a something, but we see a contrast between the blue and the red. And we call that contrast, the one that allows us to visualize or see that contrast, is space itself. Space is nothing. And space is what separates the table from the chair. Otherwise, it would be a single object. And there would be a single object in the universe if there were no contrast to each atom out there.
Oh, I thought there was only one object in the universe.
Yeah, there is only one object essentially,
different reason.
but my point here is the only reason we distinguish table from chair is that something gives the table and chair contrast, and that something, which is a nothing, is called space. So it's space that separates the two threads. Okay.
Can you pronounce brachistochrone yet properly yet?
Guy gives me a hard time about that.
Okay. I'm glad I'm not the only one.
Brachistochrone. There, I said it.
Oh, is that what I was pronouncing? And I pronounced it wrong. Black stuff on the thread. There it is again. Still farming for questions here. On what basis can there be a nothing? What allows for something and nothing?
It's not that something allows for that. That's like saying God created something and nothing so we could tell them apart. It doesn't work that way. It's just, that's our universe. That's what's out there. We have nothing, which we call space or vacuum, and we have something, which are the atoms and ropes that interconnect them. So we have the somethings and the nothing. And somethings are floating or just moving with respect to other somethings, atoms with respect to atoms, one side of the thread in the universe with respect to another side, another portion of the thread in another part of the universe, or maybe locally. So we separate these on the basis of atoms. We say this atom is made out of threads locally, and this atom is made out of threads locally, and we distinguish them because there's this space which gives them contrast, and that's the separation that we notice there. But otherwise, space is nothing. there is no physical object called space because you define the word object as that which has no shape, and that's what space is, that which has no shape.
If there's nothing between two objects,
Exactly.
they're one object, right?
Well, if let's put it this way: if there was no such thing as space, to put it this way, in those words, there's no other way to put this. Okay, if God had not made space, so to speak, we'd have a single infinite block of matter. The only reason it's chopped up is that space forms the backdrop to this thread that turns into somethings, which are the atoms, which are connected by ropes to other atoms. That's our universe. That's how simple, ultimately, our universe is.
Can a hole be a square?
Yeah, I guess a hole can be a triangle, anything you want.
Can a hole be a square? Actually, I don't think so, because hole implies 3D.
Well, it depends. I mean, if you're going to talk, we're talking about the real world, or we can even talk about imaginary world and have a black, triangle serve as a hole in a paper, okay, for example. Okay?
But no matter what.
But yeah, it's going to be right. But I mean, my point here is that
I don't think you can have a square hole.
it depends on, at that point, what you mean by
I say
hole.
no.
If you define it as a three-dimensional enclosure within matter, you say, well, this hole, this cylinder, this
Very
cube,
verbose. I'll answer that one. No. I can't understand how a mirror can reflect a laser in the rope hypothesis. How do those light ropes in the laser ray get deflected in a perpendicular angle? What do the ropes in the laser ray connect to?
other atoms. Remember, and I've got that in one of my real physics cartoons there. Every atom is interconnected. So you have a rope connected from one atom to the one over here, and now that one's connected to the side as well. When we have reflection, all you have is the twirling, torsions moving along this rope, and then being rebounded, you could say, or that atom pumps the rope that goes to another atom, and so on down the line. So that's what a reflection is. Reflection is simply the relaying of that pumping from one atom to this other atom, that atom back to another atom that's behind you, or maybe your eyes or whatever. And then you have refraction, which is the continuing. It's the rope that goes behind that atom and takes that same signal. The atom is pumping back and forth, torquing the rope, and that signal now goes to an atom behind, for example, the mirror or the glass or the wall, whatever you've got in front of you. So, what is a shadow? Shadow is that the wall stood in between you and what's behind it. And the rope is still connected because we have gravity. But that atom is connected to another atom behind it, and that's the shadow. Because now you don't have the same pumping that you had from you to the wall. From the wall to that object behind it, you have shadow. Penumbra, or whatever.
I think this is Exhibit A as to why language
is important.
Is not the language of physics. It's movies.
Illustration.
If you had a movie, you wouldn't need all that time to explain that, and I think it would have gone.
A picture's worth 1,000 words. A movie's worth 1 billion words. You look at a movie and you see the rope connected to an atom and an atom behind it. You see the movie and you say, okay, I understand that. And here's the torsion going from atom A to atom B, and from atom B to atom C, which is behind the wall, you have shadow. What is shadow? A lower frequency, a longer wavelength, because the atom is in a crystal lattice that doesn't allow it to pump at the same rate as the one coming in. But again, if you look at a movie of that, you say, well, is that what he was talking about?
Yeah, that's one of those.
A movie is worth 1 billion words.
You really have to listen close when someone's speaking in physics, because there's so many places you can get tripped up.
Yeah.
If a planet is an object, how can there be separate objects on a planet?
Well, here's an object that's on this planet. It's a separate object. But imagine every atom that constitutes this rope is connected to every object in the universe, including to you. So we have separate objects because what separates you from me are just ropes, and the ropes are intangible and invisible. So we see discreteness or touch discreteness only because we can't see or touch the mediators that connect us, that are the mediators for light and gravity, primarily those two. See, that's why I can't touch you. I can touch you, but I can't touch the mediators. They're untouchable, unseeable. Hopefully it's like that, because otherwise we would be tangled in knots. Mother Nature was wise.
Your son definitely loves football. Which team he supports? Munich? I actually don't watch football.
He's not a soccer fan. I am a soccer fan, but he's not. He's not.
I'm much nerdier than I look.
What?
Nerdier.
No, that's because of his haircut.
What gives the hole its shape? that which gives the whole its shape is an object. Oh, I guess that was clarification,
Yeah.
not a question.
Yeah.
What software do you use for your video streaming?
OBS.
What do you think about Kant?
But what?
Wait, we had that.
Oh, yeah.
Old Kantian. If motion is two or more locations of an object,
Yeah.
then an object that is spinning wouldn't necessarily be in motion?
Yeah, because when you talk about an object, you're not talking about the top. You're talking about the atom that constitutes the top, right?
No, I thought
I mean,
if an object is spinning,
yeah.
it's not necessarily in motion. But when we use the word spinning, we mean it is turning in relationship to other objects.
But what's turning it with respect to other objects? You're looking at one atom at the surface, essentially. This is what it comes down to. What you're looking at is one atom at the surface of the top. Otherwise, you would not know it's spinning. The top could be a triangle there that's just standing still as far as you're concerned. And you say, well, it's spinning. How do you know that? Well, because this atom that was on this side is now on this side. Okay?
No.
And now that atom moved with respect to something else, including to another atom in that top.
Well, we don't have to go to the atom. We can just talk about the top as a singular
How
object.
do you know it's spinning? That's what I want.
Because you have other objects in the world. That's what we talk about.
Yeah,
when we
yeah,
say
but
spinning.
how do you
If
know
a top
that?
is in space, if you have a single object in space,
How do you know the top is spinning even with respect to something else? That's what I want to know. Unless you know that one atom moved from here to there with respect to something else. You're talking about one atom.
Oh, I see what you mean. If the top is made of one.
How do you know if the top is just standing still or spinning? The only way you know that it's spinning.
I guess that's what the question.
No, but I'm putting it in reverse because this is the issue. The issue is the only way you can talk about spinning is when you talk about one atom
But then can
of
we
the
talk
top,
about-
not about the top.
But-
The top you don't know. If there's a single top in the universe, how do you know it's spinning?
Well, no, you always
It's
have
made
to
out of a
talk
single
about
piece.
it.
It's made out of a single piece. There's one top in the universe. How do you know it's spinning?
Well, hold on. If you have, that's not the question. Though.
It
The
is.
question
It gets
hold
down
on,
to
hold
that.
on, hold on.
It
If
gets
you have one object in the universe, then
Yeah.
you don't know if it's moving at all because there is no other object. But if you have two objects in the universe, regardless of what they're shaped like, you don't need to look at the atoms that comprise it.
Yeah, you do.
Why?
Because you just said it. You
Why?
just said it. Why? Because
If you
have
have
to-
one object here and one object here, and this one's doing this, we're done.
If there's a single, let's go
Single
step.
object.
Let's go step by step here. Let's go step by step
Let's
here.
go slow. Let's go slow.
We have a single object in the universe. It's a top.
Yeah.
Top. It has triangular shape, right? You typically spin it by twirling the top and the top of the top.
Dreidel, dreidel.
A little handle there. You twirl it, and now it's spinning, right? Now we have a single object in the universe, and it's a top. It's made out of a single piece. There are no pieces, no atoms. It's just made out of a single piece. How do you know it's spinning?
Well,
Wait, let me answer. I want to answer.
oh, I thought I was going to answer.
No, let me answer first, then you can answer. How do you know it's spinning? The only way you know it's spinning if you talk about two. You introduce the word two in there. Either it's spinning with respect to another object, the whole top is spinning with respect to another object, or one side of the top is spinning or change its location with respect to an atom, a component of the other side of the top. You're treating a little piece of the top as it changed location with respect to the first piece. Again, you got two. You no longer have one. It's like you're treating it mereology. What you're saying is the top is made out of atoms. It's spinning because this atom is no longer on the left. Now it's on the right, and the one that was on the right is on the left. That's why you talk about spinning. The only way you can talk about spin is if you talk about two atoms, and in that case, one atom is moving, has changed location with respect to the first
I
atom.
think it's a loaded question because the question is, how do you know it's spinning? That implies we're
I don't know. In science, we do not know. In
it's
science,
a-
we
it's a
define.
loaded- it's a
And
loaded
we
question.
No, we define the word motion, and there's no provision
That's
for
what I'm saying.
observer.
That question doesn't really
It does
fall
because
into science,
we
does it?
just
How do you know that the top is spinning?
yeah
Is
we
a
get rid
science
of the
question.
no part. We say in science we don't know. We don't use the word no
Okay,
because that's observer, and we don't have observers in science. What we have to define what we mean by motion. Motion requires two whatevers.
Yeah.
And in this case, if the top is spinning, and we're going to say spinning is a verb meaning motion, the only way you can conceptualize it when there's a single top in the universe where it's made out of a single piece, one atom has to move with respect to another atom, or one
You need
component
two
or whatever.
objects. You need
You
two
need two.
objects.
You need the word two.
Ever read Hegel? He's
Yeah.
fun to read, Philosophy of Nature, but I'm sure you get something along too.
I read Hegel primarily through Marx because I used to be a Marxist a long time ago, and Marx introduced me to Hegel, and I had to read Hegel to understand Marx because Hegel was Marx's teacher.
Does the thread have shape in the context of the universe it makes up?
No, again, the only way the thread has any relevance is if you talk about another a parallel universe, a multi-universe, then you can talk about existence, speculate about the possibility of another universe that's not connected to ours. You can say the speed of light is different over there than the speed of light here. You can speculate a lot of stuff that's interesting. And again, it's speculation only. It's nice to talk about these things. Otherwise, the thread has no context whatsoever, especially when we talk about the word exist in relation to the thread, because then you're not talking about the thread, you're talking about the word exist. And again, I can make my thread exist immediately by just putting another thread. And then we solve the problem of existence of the thread.
An issue remains in space itself, i.e. the basis of location. Why will two objects not occupy the same location? Why will one object not be in two locations? Zeno's paradox as well.
Well, again, when we talk about the thread or the rope and the thread can go through each other. I covered that the other day to some degree, and I'm sure there's a lot of questions on that because that's one of the tricky points that people are concerned about as far as the rope hypothesis. So they can go through each other. And the question here is, does an atom go through another atom? The answer is no. And you say, well, why is that the case? Why can the thread go through a thread? And here's the atom made of threads. You know, we have the proton star is made of threads. The electron shell, the membrane, is also made of threads. And you say, well, hold it, you have threads and threads. Why can they go through each other here, not over here? And again, it's got to do with what I say is agglomeration. How do we, if you look at a table, if you could have your telescope, your microscope, God's telescope or God's microscope, you would see it's made out of gazillions of atoms. You can't see one atom, but you can see the table. How is it that you can see a table with stuff that you cannot see? Agglomeration or accumulation. What's happening, you can see many atoms, but you cannot see one atom. And you can see many ropes, maybe, probably not, but you can't see one rope. Okay.
Well, many ropes of light, I guess.
Yeah. Well, again, yeah, and that's. But you see the effect of light, not the mediator of light. So that's the issue.
I guess.
You see the
we don't
the
see
bump.
ropes.
No,
Yeah.
you don't see the rope. You'll never see the rope because the rope is unseeable. You're talking about something so thin compared to an atom. We can't see an atom. Here you're talking something so thin with respect to an atom. You're not going to see the rope. And again, the only way you can see the rope essentially is its effect in an atom, which is the little thump it gives when the torsion arrives at the atom, and you take many of those, and now you can see the wall. Otherwise, you would not see the wall. You would not be able to see one rope hitting one atom on the wall. You wouldn't, if that's the only thing that God made in the universe, you would not be able to see that atom in that rope. The only way you can see the wall is by putting all these atoms together and saying, oh, now that I have gazillions of atoms, now I can see the wall or the table or whatever you're seeing. So yeah, and again, all I'm saying is that atoms collide against atoms because now you have many threads that make up the membrane. Membrane suddenly brings the thread into the touchable world, into a world that we can touch and see. If you just get one thread, you can't see it or touch it. But if you have many threads, it becomes an atom, and when you have many atoms, now you can see and touch, you know, the objects that. In other words, what happens with the thread? It acquires tangibility and seeability, visibility, only through aggregation.
Is it correct to say that a thread by itself has a fraction of tangibility?
Yeah, I think there's some friction at its level, but you're talking about something so thin, unimaginably thin, and it's got a property that we don't have in our tangible world, which is objects going through objects. And you say, well, how come in our real world we can't have tables going through chairs? And you're telling me that the thread in its world, in its Planck length world maybe, or even smaller, how come a thread can go through another? Well, because in that world, it does function a little differently first. And you might say, well, Bill, you just did that to cheat so that you can get away with murder. And no, it's the real world that Mother Nature has out there. I mean, I can't pass my hand through this in our real world. But obviously, you know, I can take two laser pointers, you know. I can take two laser pointers and the light goes right through each other. You know, you can do this on your own. Don't trust me. You take a laser, you turn them on, okay? And you shine the lights right through each other, and it's not like when you take two showers, you know, and run the water, or two hoses, and run water through each other. You'll see that the water droplets go in every direction. That's not what happens to light. There is no sparks, you know, from the collision of photons.
Yeah, photons also.
And so you have to explain. You have to explain that. You got to say, hold it. Mother Nature's world works a little differently, and quantum has accepted that, where light goes through light. Photons go through photons. Threads go through threads. That's the world you have to explain. And if you're going to explain that, you have to make an assumption. You have to say, well, there's a thread, but the thread has the ability to go through each other, and it only cannot go through each other when it forms, there's a whole bunch of them forming an electron membrane. Now they invented tangibility as we understand it in our macro world.
I'm not sure what the context is on this one, but
Okay.
just ask it how it's asked. Did he answer what his criteria he uses to show shape? He still thinks that object equals has shape.
Yeah, this is the context, okay? Let's get the context on shape, because people say, okay, what did you mean by shape? And they go on and on and on and on. And nobody asks, what did you mean by that? Or what did you mean by which? What did you mean by has? You know, that which has shape? Why didn't you ask those questions? And people don't ask those questions because it's like the key word is shape. But it's much harder to define the word has, the word that, the word which, than the word shape. But that's not the issue. Here's the issue. The issue is that physics cannot be done without an object. We need to define the word object for the purposes of physics. And the issue here is what criterion or criteria are you going to use to define the word object for the purposes of physics? That's the issue. That's the context. That's what we have to. We've got the door locked. We have this conference here, and it's 8 billion people inside the conference room. We will not open the doors. We cannot leave until we define the word object. The question is what criteria are we going to use to define the word object? Are we going to say see, touch, which is what mathematics uses today? They say anything you can see or touch. Are we going to use volume? Are we going to use mass? Are we going to use subject of a sentence, exist? What are we going to use as a criterion? And we're saying that the criterion is shape. It's the universal property, the property that all objects have. There's no such object that doesn't have shape. And so that's the criterion. And so when we talk about shape, it's not a question of playing devil's advocate and say, well, what did you mean by shape? No, all we need to know is, do you understand the difference between shape and motion? Do you understand the difference between shape and mass? Do you understand the difference between shape and touch? Because we have to choose a criterion for the word object for the purposes of physics. That's the context. So we don't need to badger the guy and say, well, what did you mean by shape? You want to know what shape is? Very simple. Just go to a kindergarten, and the kindergartners will teach you what shape is. And it goes like this. You show them a cube, and you show them a ball made out of the same material, same color, same everything, except what? And you say to the kids, what's the difference between this and this? And it's a shape. And you'll know what shape means. And that's what the criteria that we use. We use the simple criterion known as shape.
I'm sure you know the context of this because it goes over my head. I have a question about accelerated expansion. The farther away a galaxy is, the faster it recedes from us. Therefore, acceleration. But the opposite. The closer, the slower expansion. Why not deceleration? In other words, why is the idea of a slowing acceleration ruled out?
I have a different take on that, completely different take. Some of you heard of Halton Arp, and he was a guy who was an astronomer. He had to leave the United States. He was hounded to extinction almost. He died a couple years ago. And he said, look, the redshift is not a measure of speed away from you, like a Doppler effect. This is not a Doppler effect. I refer to it as tired light. I didn't invent that term. This term was already around. And what it is this redshift that these people are seeing in the universe are along the lines of what Mr. Arp explained. Okay, and it goes something like this. If you look at a rope, take a rope, any rope, and tie it from one post to another. Like take your grandmother's clothesline, if she's got a rope, okay? It's got to be a rope, a two-stranded rope, one tied around each other. Otherwise, do it yourself. Just tie a rope between two posts. And you will note, and tie it as tight as you can, make it as taut as possible. As you walk away from the post to the center of the rope, you will see that the links are getting longer, okay? Nothing changed. There's no motion. The rope is just static there, just standing there. And you will note that if you were to measure, maybe you won't see it in a short rope, but a long rope, if you measure the links, you'll find out that they get longer and longer. And that's what this experiment in the Harvard Tower showed, that when the guy was in the basement and he shot the light to the top of the tower, they said the links are getting long. They said the frequency changes. And under the rope model, very simple, the links are getting longer the farther away you get from the center of the Earth. Very simple. What's happening with the galaxy? Same thing. When we're staring at a star, you're staring at a galaxy, it's not that the galaxy is receding from us the farther it is away. It's that the farther it is away, the links get longer and redder. That's why the universe looks red to us.
Everything's just so far away that the link distribution happens to fall into the red area. Right,
and so it's not that galaxies are receding for some magical reason away from the Earth, as if the Earth were the center of the universe. It's that the farther a galaxy is from us, the links get longer, and that's called the redshift. That's one issue. The other issue you should keep in mind is that the blue-shifted galaxies are the ones from the local group, which are 50 or 60 galaxies today that they found in the area. And you take one like Andromeda Galaxy, and it's coming towards us. It's blue-shifted. And so you say, hold it, how come all the galaxies out there, the ones that are farther away, are all redshifted? And this guy that's only barely 2.2 million light years away is blue shifted. It's coming towards us. Why? And it's that this one might be coming towards us momentarily because, these galaxies are going around each other. They're moving. It's like one comes closer, then goes farther away, and so on down the line. And so what happens? What happens is that when you talk about local galaxies, some of them are blue shifted because they could momentarily be coming towards us. That is a blue shift.
But that's
Doppler, that's a Doppler shift type situation. The ones that are very far away, that's totally irrelevant to the Doppler shift. It's not that it's coming or going. It's that it's so far away, and the farther away it is, the redder it is. It's not that it's going away at a faster speed away from us. It's that because it's farther away, the links are longer, and that's why it's redshifted or more redshifted than some of the closer ones. That's all it is.
Questions. Since we are the last generation of humans on Earth and the money is no more, why does Bill write and sell his books?
Because I'm crazy.
You want to collect the magical Disney dollars.
No, the issue is that it's not so much about selling or anything like that. It's that if you give it away for free, nobody reads it. That's the issue. And
That's true.
I found out that on and on and on. I've given books away for free to people, and when I ask them, what did you think of it? Oh, I haven't read it yet, or you can tell he hasn't read it because he can't answer any question.
One of my friends has your book, and he uses it as a desktop razor.
I don't doubt that for a moment.
Because it's so thick.
A paperweight.
If there's only one object in the universe, the top, is not the universe the top?
If the universe were a top, the universe is a concept.
This is when we're talking about
Yeah. And what about it?
If there's only one object in the universe, is that object not the universe? I guess.
Well, remember the universe includes matter and space. Universe is a concept, and it's built of two, and two is always concept. Okay.
Two objects, but the space isn't an object. So
we treat space as an object, or again, the definition of the word concept is a word that includes two objects or two words treated as objects momentarily.
So
in
we
this case,
reify space in that case?
in that case, we treat space as an object. We say there's two objects in front of us. There's this black stuff, which we're going to call space, and we call this top, which we're going to call the object. Okay, so there's two objects. That's what space is. Two objects. It includes two words: object, the object in this case, the top, and space. So universe is the wrong word. Universe is always a concept, no matter what, and it includes space and the object that's in there that you pointed to, in this case the top. So you can't say that the universe moves or that the universe is the top. No, the universe is the top and space, always.
Is magnetism made of atoms?
No, magnetism is made of threads. That's, in other words, a magnetic field, so-called field, that is a concept, is swept by threads. And again, the way we explain like attraction between two magnets, and I've got that illustrated again, that's in fact, I have it here. Let me get it, because that's what it is. If I can find it here, where is it? The field of evidence, it's around here. Here it is. Found it. Here it is. Picture's worth 1,000 words. Oh, where'd it go? Right at the bottom. When you push it too far up, it goes to the other side. Okay, there it is. That's the magnetic field, what you're going to see there. Threads moving around. If they move against each other, you have push. And when they're going in the same direction, you have pull. Okay, so if you stare at that for 2 seconds, you'll see what the mechanism of a magnetic field is. Here you have north against north or south against south, and they're going to push each other away because one is going clockwise, the other one counterclockwise. When you turn the magnet around, okay, now you see south against north or north against south, and now they're going in the same direction, and one pulls on the other. That's the mechanism, the physical mechanism of attraction and repulsion. And what we're saying is the magnetic field is swept by, in other words, what's in there in that invisible area are the threads. That's the physical entity that's producing this effect. Let me pull it out.
Yep.
Okay, put it up here. Okay, we're back.
Why not define philosophy as rational explanations of thinking instead of behavior? Is that fine? I can also define it as that.
No, the answer is no, and the reason is we all think. So we have 8 billion philosophers, and then we would not be able to distinguish between Aristotle and you, because everybody's a philosopher. Now, if we're going to use the word philosophy in such a way like saying, oh, I studied philosophy in college, or Aristotle is a philosopher, we have to know what we mean by the word philosopher. We can't say he's just a thinker. We're all thinkers. So it's too general to say thinker or whatever,
I think that's it for the questions.
Okay. Well, then we'll see you again on Wednesday. And if you put comments there and questions, we'll try to answer them next time around. We'll see you then. Bye-bye.
Bye, guys. Be back next month.